Hey everybody, it is Mr. Sharkey. Welcome back to another exciting chemistry video. Today we are looking at the percent yield of a chemical reaction notes page. So if you have your notes with you, go ahead and flip open to it. Otherwise, I've provided a copy for you online. So last class we started looking at BCA tables, which stands for before, change, after, and we were using those to predict the amount of product that we could create during a chemical reaction. However, an important note that we were looking at last class didn't really matter back then, but now it does. In a BCA table, we can only use the unit that we were using last time, which was moles. However, if you think about our experience in the chemistry classroom, there is no way for us to go to a counter and weigh out the number of moles of a substance that we need. In fact, most of the time when we go to measure something out, we're only going to be able to measure the mass of that substance. So that means that when I am given a question in real life, I'm going to have to take the mass of the substance I'm concerned with, and I'm going to have to convert it into moles before I can do stoichiometry or my BCA table. That's the tool we're using right now. So that brings us to this idea of a percent yield. This is how we're going to take stoichiometry and we're going to use it in the real classroom. So there's yield. This is a term that I'm hoping we're familiar with. We talked at the beginning of this unit, or I guess really last unit, when we were balancing chemical equations. This arrow has a special name. This is called a yields arrow. And that's because the word yield literally translates to a yield is what we make. So there's a few different types of yields that we are going to be looking at together. The first one is called a theoretical yield. This is the amount of product I'm going to rephrase here. This is the amount of product that we can make in the reaction. This will always be calculated in a BCA table. So this will never be given to us. This is something that we actually have to calculate. We are given the starting parameters of the reaction, and we can figure out how much of the product should we be able to make. The next type of yield is called the actual yield. The actual yield, this is the actual amount of product that we did in fact make during the reaction. This will either be given in the question, or if we're doing a real life example, we'll do this in lab either later this week or next week, we have to find this in the lab. So we'll either be given this information, which is what we'll see in our example question here in a second, or again, if we're in the lab, we have to calculate it. So that brings us to our final type of yield, which is called a percent yield. What a percent yield is, it is a percentage calculation of our actual yield versus our versus our theoretical yield. So what we're doing here is we're comparing those two numbers to each other, and it kind of gives us an idea of how well we did the lab. In an ideal situation, you would get a 100% yield every single time, but by nature of us making measurements, those things never really turn out that way. We hardly ever end up with yields that are really like 90-ish% that's kind of great work. In a high school lab, I would expect us to be closer to 70, just given the materials that we have and the skills that we're still working on in lab. So we've got these two different types of yields. I'm going to do a little color coding here. So theoretical yield and then our actual yield. And if I want to find the percent, I'll take the actual yield divided by the theoretical. If I just do that calculation, it comes out as a decimal. So to turn it into a percent, we multiply by 100. So let's look at an example question. When we get to these example questions, remember our BCA table requires moles. And when we're reading this question, we need to try to determine what information we've been given and when we're going to need to use it. So what I see here, nitrogen gas has 112 grams, and it reacts with hydrogen gas to produce 40.8 grams of ammonia. So the way that I'm interpreting this question, they're telling me that we have actually produced 40.8 grams. So this is our actual yield. I can't use that to find my percent because we don't know the theoretical yield yet. What I see in this question is that it tells me when I did this reaction, I started with 112 grams of nitrogen. But that is not in moles. So I can't use that number yet. Before I use this 112 grams, I need to convert it into moles. So I'm going to do that first. That's going to be my very first step. I need to convert my reactant to moles. So if we remember our mole calculations, we could look at the backside of our periodic table. 1 mole is 6.022 times 10 to the 23rd of whatever particle we're talking about. And that equals the molar mass in grams. What I like to do, and I would encourage you to do this if you're not already doing so, when I have a question, I like to go ahead and highlight the units that show up in my question. So for instance, I see grams shows up here. I'm going to highlight that one color. Here I've got yellow. And then I also see that I'm going to need moles, so I'm going to highlight that in green. And then to figure out what parts of my conversion factor I'm going to use, I'm going to come back in here and I'm going to highlight my conversion factor wherever I see the similar units. So in my conversion factor, it says 1 mole. I'm going to highlight that in green. In my conversion factor, it says the molar mass in grams. I'm going to highlight that yellow. So in order to do this conversion, I need the fact that 1 mole equals the molar mass in grams. So that means I need to find the molar mass for nitrogen. Luckily, they've already given us our balanced chemical equation. So we can look at this. And I'm just looking at the formula for nitrogen. It says that it's N2. So if I want to find the molar mass for nitrogen, which has the formula N2, I look up the average atomic mass on my periodic table. If I have one atom of nitrogen, it has a mass of about 14.01 AMU, or 1 mole would equal 14.01 grams. But there's 2 nitrogens in my N2 particle, so I multiply that by 2. And I would see that 1 mole of N2 equals 28.02 grams of N2. And this is the conversion factor that I need. Here's my molar mass, and that is equal to 1 mole. So it doesn't matter if you're using dimensional analysis or proportions, you're going to end up doing the exact same math either way, but I like proportions, so that's what I'm going to do. If I have 1 mole of N2, I have 28.02 grams of N2. That comes from my conversion factor. So in the proportion method, I'm going to set up another ratio, and I'm going to say, how many moles do I have, because that's what we're looking for, if I have 112 grams of N2. From here, I need to cross multiply, so I get 112 times 1, which is just 112, equals 28.02 times x. So in order to get x by itself, I need to divide both sides by 28.02. And if I do that, I'm going to round to 3 sig figs. I get 4.00 moles of N2. So that's just my first step. In my second step, I'm going to use a BCA table to find my theoretical yield. So to do that BCA table, I start off with my balanced chemical equation. If I have 1 mole of N2, it will react with 3 moles of H2 to produce, 2 moles of NH3. B stands for before, C is change, A is after. We just found out we're starting with 4.00 moles of N2. In the question, it did not tell us how much H2 we have, so we're going to assume that's excess. And then I like to divide my BCA tables with a line to remind myself that the reactants and the products behave differently. So one of those differences are products. We usually start with 0. From here, I know that I'm going to use all 4 moles of N2. So by the time I'm done, I will have 0 N2 left. And this is the starting point of our BCA table. Now, I'm kind of going to go crazy with highlighters again. So I'm going to reuse a couple colors, I think, eventually, because I'm going to have to. But let's say we're looking at this N2. And we want to figure out what is the change in H2. Well, in order to do that, we have to use a mole ratio. So if I look at that balanced chemical equation, it says if I have 1 mole of N2, then I would need 3 moles of H2. That's if I'm following the recipe exactly. But we aren't following the recipe exactly. We're looking at this change section, and right now we don't know how much H2 we're using. What we do know is that we're using 4.0 moles of N2. So we can set up a proportion, or again, you could use dimensional analysis if that's your thing. And I'd say if I'm using 4.0 moles of N2, then how many moles of H2 would I need? So I'm going to highlight here just so you can see where these numbers are coming from. So my solid orange box, that comes from my balanced chemical equation. I always keep that paired with my solid red box. So I'm comparing the N2 in the chemical equation to the H2 in the chemical equation. On the other side, I'm just doing kind of this orange outline to show that that number comes from the change section, and a red outline to show that that number also comes from the change section, and I'm comparing those to each other. So what I can do is I can cross multiply or solve for x however your algebra feels fit to do so, and then we'd get 1 times x, which is just x, equals 3 times 4, which is 12. I'm going to keep 3 sig figs, so it's 12.0 moles. So in this part of my BCA table, I would put 12.0 moles. Because this is a reactant, we always use up the reactant, so the change is negative. So when I'm done, we'd take whatever excess we had, we'd subtract 12.0, and that's how many moles of H2 we would have left over. So finally, let's get to the last part here. Running out of colors, I'll use this darker blue as opposed to the lighter blue I used earlier. So if I want to find the change in NH3, I could follow this exact same process. This is called a mole ratio. So if I look at my balanced chemical equation, it says if I have 1 mole of N2, then I have 2 moles of NH3. I'm going to set that equal to the change section. In the change section, I'm actually using 4.00 moles of N2. So we can figure out how many moles of NH3 we need to do the reaction. I'll highlight again just to show you where my numbers are coming from. So the first ratio is always coming from my balanced chemical equation. I'm just comparing the coefficients that are out front. The second ratio is always coming from the change section. To solve for x, I could cross multiply. 1 times x again is x. 2 times 4 is 8. With 3 sig figs, that'd be 8.00. So when I'm done, I would have 8.00 moles of NH3. I'm producing that, so it's a positive change. So 0 plus 8.00 is 8.00 moles of NH3. Sorry, I'm going to go back to highlighting. If we look up above, I had highlighted the theoretical yield gray. So I'm going to highlight my theoretical yield gray. So this is my theoretical yield, aka my TY. But you might notice an issue. If we look up at the question, our actual yield was 40.8 grams. Our theoretical yield is 8.00 moles. I'm hoping you see the problem. One of these is in grams, the other is in moles. In order to compare those two, we need to get them into the same unit. So the final change that I'm going to do, I'm going to take my theoretical yield, which is currently in moles, and I'm going to convert it to grams. So I could look at my mole conversion factor. 1 mole equals the molar mass in grams. Those are the only two pieces I need because I see moles and grams are the units that I'm looking at. So if I have 1 mole of NH3, I would need to set that equal to the molar mass of NH3. Nitrogen is 14.01 grams per mole. Hydrogen is 1.01, but there's 3 of them. So if I add all of that together, I would get 17.04 grams of NH3 for every mole. So again, I could set up a ratio. If I have 1 mole of NH3, then I would have 17.04 grams of NH3. But I don't have 1 mole of NH3. We don't know how many we have. Oh, I'm so sorry. We do. We have 8.00. What we don't know is how many grams that is. Sorry, I got mixed up at where we were in the question. Again, we can cross multiply. 1 times x gets us x. 17.04 times 8.00 rounded to 3 sig figs gets us 136. So that's how many grams of NH3 we have left over. And again, this is our theoretical yield. So now we have our theoretical yield in grams. We have our actual yield in grams from the question. We are ready for our final step. Sorry, I guess I should add in here. Step 3, we had to convert the theoretical yield from moles to grams. So finally, step 4, we are going to calculate the percent yield. Percent yield is the actual yield divided by the theoretical yield times 100. So in this case, all we have to do is take 40.8 grams and divide by 136 grams, multiply that by 100, and if you plug that into your calculator and round to 3 sig figs, you would get 30.0%. And that is our final answer. Whew! We did a lot of work. But some of that time was reviewing an old skill. So for instance, question 1 here, this conversion is something that I'm hoping you remember doing last semester and you can do quickly. Our BCA table is what we learned last class. I didn't need to fill out the whole thing, but on tests and quizzes we're going to ask you to, so I'm just getting that practice. I think it's good for you to get that practice. Make sure you can answer any question I could theoretically ask you from that BCA. And then step 3, that's really just another mole conversion. So if you know how to do mole conversions, if you can do those quickly, it basically eliminates half of the work that I just did on this page. But we are spending some time working through it together to make sure you guys are prepared. So that is the end for this notes. Be sure to check the module for what else you're doing today. Thanks, everybody. Bye.